But I really wanted to give you kind of an overview of the things that we have focused on, starting from our earliest work, which I am going to introduce just as a sort of foundation for the work that followed, and how we applied it to printing conductive inks for electronics. We've done work in microbatteries, which I won't talk about. Some of our earliest work in 4D printing, which I think started to kind of catalyze the ability to encode not only three-dimensional space, but how these materials might transform as a function of time, the fourth dimension. I will talk a little bit about our work in liquid crystal elastomers because I think it's a really fascinating material system, and I'll talk about why I think that's true. If there's time at the end, we might do a little whimsy, which is how do we make these like locomotive soft robots using multi-material, multi-nozzle arrays. We've done a lot of work in sort of organ-on-chip models and building cardiac and kidney tissues for therapeutic use. But again, I don't think there's time to really cover all of that. So I'm not going to talk about that. And in fact, I'm not going to talk about really anything in our embedded printing space. Although complementary to everything that we've done with direct extrusion, we've done a lot of work where we're extruding functional features inside materials. So we don't have to print the entire object, but just print the functional part. For example, microvascular networks, which were central to autonomous soft robots shown here, which also allow us to encode not only open channels for pneumatics, but also sensory apparatus for robotic soft grippers. Again, I won't talk about that. To basically vascularizing highly dense, cellularly dense tissues. So that really has been another key aspect of our work that I won't describe. I'm a material scientist by training, and for 20 plus years at the University of Illinois, I ran a lab that basically only focused on soft matter. But when we came up with this discovery of being able to embed microvascular networks in self-healing polymers, a light bulb kind of went off for me. I said, wow, this is something that I know the tissue engineering community really needs, and we might be uniquely positioned to kind of move the field forward if we brought some of that into to bioprinting and tissue engineering. And so over the last 10 years at Harvard, we've kind of expanded beyond materials into that domain. But again, I apologize, I won't really talk about that work today. I'll talk about more from the material science foundational approach that we use for everything we do, whether it's materials or biology. And if you're in the field of material science, you're very familiar with this diagram. It came out of a 1990s NAS study, a decadal study on material science led by Mert Fleming at MIT at the time. And it was basically this paradigm which says that the way you process a material, it controls its properties and structure, so that you can't independently create a certain set of properties. It really depends on the processing and the structure that evolves over time, and that all combines for performance. And as a material scientist, I became really interested in 3D printing from the perspective that, unlike bulk fabrication methods, things like injection molding, extrusion, et cetera, where you get a monolithic, compositional, uniform part, 3D printing really allows you control over a composition, structure, and properties across multiple length scales. And so that was really what moved me into this area, and where we've obviously spent a lot of time over the last 20 plus years. So we've been fortunate enough to basically pioneer, I would say, 3 printing methods. They're shown here. This one that this video is playing is called direct ink writing. It's essentially extruding a viscoelastic material through a nozzle. You're going to hear me say that word viscoelastic a lot. The reason why the viscoelasticity is important is because it allows you to maintain filaments. There's no wetting and spreading like in inkjet printing when you're printing a low viscosity fluid that a droplet impinges on a substrate and spreads. So here you can see that we can keep a filament in its filamentary shape. We can do that in just directly printing in air, or we can do that by printing inside a matrix. And this was really the key paper that allowed us to move into the tissue engineering space. One of my former PhD students, Willie Wu at Illinois, discovered a way to pattern vasculature inside a hydrogel. This was an acellular matrix, but at the time, it was our sort of light bulb moment. You can see this branching architecture. We can control the filament size simply by either the speed at which we translate the nozzle or the pressure we apply as the nozzle is translating to sort of thin this filaments, much like you do in your capillary and blood vessel network internally. And then more recently, a very talented postdoc, Mark Schuyler Scott, who's now on the faculty at Stanford, built upon this concept and came up with this idea of SWIFT, sacrificial writing in functional tissue. The idea here now is to replace this hydrogel granular matrix with building blocks that are cellular. So these are densely cellular, human cell-laden spheroids, multicellular spheroids. And you can see as the nozzle translates through them, they can easily move out of the way. So they have a self-healing capacity. But once we warm this tissue up, this ink can be erased, and the matrix around it, which is cell-laden, basically solidifies, allowing us to remove everywhere you see red ink becomes an open channel, and you can see these inlet and outlet perfusion pins that allow us to basically perfuse and keep this very dense tissue alive, without which the cells would die. So that's the basic idea of the methods that we've pioneered, and then we have on top of that, and in fact, all of this kind of motivation and inspiration came from a time that I was at Dave Waits' lab. I took a sabbatical in 2004. I met Jacinta Conrad there and was fortunate enough to get her to come to my lab. But you know, they were pioneering these beautiful microfluidic methods. And we came there with the intention of trying to bring in microfluidics and these kinds of concepts into our print heads. And with that comes, I think, the ability to enhance the complexity of the things that you're printing simply through the nozzle designs. So being able to switch materials quickly, and you can see this at scale in a 4x4 nozzle array with multiple materials at this outlet. You can see core shell printing, which if I have time, we'll talk a little bit about. But then we've used that to, I'll start this movie, to do what we call rotational 3D printing, where we have multiple materials where we can actually structure the filaments, and I'll give some examples of why that's useful. And then we also have these adaptive nozzle arrays, basically like skiing over moguls. Each nozzle is moving independently so that we can print on non-curvilinear surfaces. So at the heart of everything that we do is actually a very simple concept. Everybody this morning brushed their teeth. They extruded toothpaste out on their toothbrush. When they applied a certain pressure, the toothpaste flowed, and when they stopped applying pressure, it kind of set on the brush. That's essentially a very simple example of a viscoelastic response. Above a characteristic yield stress, you get flow, and it's shear thinning. The harder you squeeze, the lower the viscosity. But the minute you remove the stress and return to a solid-like state, it essentially allows you to keep this filamentary architecture. And so with that in mind, we have essentially done this for a myriad types of materials, where we've engineered in this internal structure or interactions that cause the material to have a solid-like response under quiescent conditions, but then shear yield when you apply an appropriately large force. So with that then, I'm going to highlight a few examples, including colloidal gels, which is, like I said, our earliest foray into designing inks for printing, polymer inks, and then this is actually our multi-cellular spheroids. You can see that these are actually living because each one of these spheroids is beating. They're made of cardiomyocytes that have been derived from induced pluripotent cells, human cells, and when we print with these, then we can create a three-dimensional, large-scale cardiac tissue that ultimately fuses together and beats in unison. JC put together this background. If you can see all of these figures in the light, I don't know, I can see them up here. I'm not sure you can see them here, but she did this for a recent celebratory talk that she gave to convince people that I really was a soft matter person. Because we do a lot of rheology. And I'm not going to go through all of the mechanisms and ways that we can trigger this viscoelastic response, the transient yielding that I described, and the resolidification. I'm only going to highlight sort of examples in colloidal gels and direct printing of elastomers today. But there really are underpinning all of the work that we've done, multiple schemes for inducing this resolidification, both in the inks that we're printing and in the matrices that we're printing into. So the earliest work really started as part of a sabbatical that I spent at Sandia National Labs, where I got to work very closely with Joe Cesarano, and one of my PhD students also spent time in his lab. And that was the genesis for extrusion-based printing. And the idea here is to take colloidal particles. In this case, we're working with silica. And in the absence of any kind of surface coating, silica is a negatively charged particle over a broad pH range. Its isoelectric point is actually a pH of 2. When we functionalize this with polyethyleneamine, which is an oppositely charged cationic polymer, these particles become very highly stabilized. We can go to high volume fractions, which allow us to engineer and build in a stiffness, an elastic modulus that allows them to span, be spanning. But when we change the pH, we can go from a fluid to a gel. And that is what we use to sort of tune the G prime, the shear elastic modulus, or the solid-like response of this material. And then working with JC, we tried to understand fundamentally what is happening in our printheads as in these nozzles as these particles are flowed through our nozzle. And so we made this very nice sort of mimic of a nozzle, a microfluidic device. And you can see that these little particles, we can actually introduce fluorescent cores. We can track them. And this is just looking at an edge in a region where you're turning down from, say, the ink barrel to the nozzle. And you can see that under shear, these particle clusters start to break up. But when you take the shear away, they rebuild very quickly. And this spanning network is really what's giving it its solid-like properties. So we then did some work to show that because of this ability to engineer the elastic moduli, we could span very large gaps, and we could tailor that with respect to the value of the sort of shear modulus, that particle-particle interactions. And we showed that then taking these inks, we could make these nice, beautiful lattices. And as I said, this is very, very old work, but you can see the uniformity of these features even as they're spanning very large gaps, right? This is just a surface profilometry scan. They're all very nicely uniform. They're not slumping. And that really led to the work that I'm showing here, which is a collaboration that we were very happy and fortunate to have with John Rogers at Illinois before I left. And you can see that this is actually a nozzle that's translating, that's coming out of plane and up to a step ledge. And we can use this then with these silver nanoparticles now. So we're replacing silica both with a smaller size particle and a functional particle, a highly conductive particle. We're still coating with polyelectrolyte, and we're able to induce this viscoelastic response in such a way that we can span gaps and create these electrode arrays in a planar configuration to wire up micro LEDs. And these micro LEDs really are pioneered by John Rogers' lab. And each one of these micro LEDs has these little contact pads, which is what we're connecting our inks to. And then you can see these outer contact pads that allow us to then come down and light up individual LED arrays. So more recently, we've taken that same kind of material and we've built a little bit more sophisticated electronic devices. Again, here I'll just show something. Shifting gears, the next part of the talk is going to focus on some of our polymeric ink and matrix designs. Again, we've done work, everything from like polyelectrolyte complexes and hydrogels, which were sort of a precursor for some of our bioprinting work, to elastomers and even thermosets. Today I'm just going to highlight pure elastomers and liquid crystal elastomers, where here in the second example, we're going to use the shear-induced field to align rigid mesogens along the backbone of these elastomer architectures. All right, so this is kind of just a snapshot of things that I'll talk about. I'm going to begin with pure elastomers, where we're simply controlling the architecture itself, not the material, to elicit a range of mechanical responses. And then I'll talk about our ability to use rotational 3D printing to integrate stiff and soft elastomers in interesting ways and control at sort of a sub-filament scale the material properties. And then I'll go to some liquid crystal elastomers. And this work was actually motivated in part by that earlier work that I showed with that shape-morphing flower, which was a hydrogel with cellulose fibrils, and some more recent work where we used short glass fibers to create these three-dimensional structures that morphed into 3D, from 2D to 3D transformations in shape by controlling the alignment of these fibers. And that led us to start thinking about whether or not, even at a molecular scale, we could encode alignment using printing, and what that might end up resulting in terms of shape-morphing capabilities. So early work, shortly after we came to Harvard and kind of expanded into printing soft elastomer materials, we were fortunate to work with Ole Sigmund's group in Denmark at DTU, and he had a visiting student that came and spent a year plus in our lab. And the idea here was to create target designs where we could systematically vary the Poisson ratio of the architecture and have it be constant over large strain values, so using nonlinear designs. Typically what had been published to date were ones where you could dial in specific Poisson ratios, but as you strain the structure, they changed. They weren't constant. And so on top of this ability to dial in systematically a specific Poisson ratio, we also wanted to make sure that whatever design was computed by their group, which is a computational group, could actually be printed. So that was the second constraint. Is it printable? Is it manufacturable? And so in this case, we used these elastomeric inks. These are PDMS materials that we designed to be printable. We can vary the ratio, the stiffness, by changing the base to catalyst. We can make them colored if we need to do that. And we can dilute them with things like silicon oil. And in this case, we just used a standard formula without. These are transparent. And simply by changing the lattice geometry, we could dial in specific Poisson ratio values. And just for reference, the bulk PDMS has a Poisson ratio close to about 0.5. And you can see now us printing this architecture here, which has a negative Poisson ratio of -0.8. These are 2D architectures, which is why you could go actually over this broad range of values. And we, of course, have introduced in these unit cell configurations different modalities. So rather than essentially most materials, as you put them under tension, they contract in the lateral orthogonal direction. These can expand, as you can see, when you have a negative Poisson ratio. And I'll show you that in detail in the next slide. But a priori, we can essentially design over this broad parameter space simply by changing the unit cell architecture this range of values. And so you can see this very nicely here, how the unit cell design changes, and then concomitantly how we get a variation in the Poisson ratio. And then as this structure is expanded under uniaxial tension, it is also expanding in the lateral direction, which is why you have this negative Poisson ratio. But as we go to different lattice dimensions then, or lattice unit cell designs, we can dial in anything from -0.8 to 0.8 in terms of the Poisson ratio. And of course, using things like embedded printing, which I'm not going to talk about today, one can take this into the third dimension. And of course, there's work here by Tim and others that are doing beautiful three-dimensional architectures. But I think this was kind of one of the earliest embodiments of using printing to a priori design and control and program the mechanical response. And then I had a very talented set of postdocs, Jordan Rainey, who's at Penn now, and Brett Compton, who came shortly before Jordan, and they designed this rotational printhead, and they were doing fiber-filled composites, so for structural applications. And then Jochen Mueller, who was a visiting student in my lab from ETH Zurich, from Christina Shea's group, also got involved. And that work was really the precursor for this rotational multimaterial nozzle that was led by Natalie Larson, who's also a very talented postdoc in my lab, who's now on the faculty in mechanical engineering at Stanford. And the way this works, I'll play the video in a minute, but this is the complex nozzle design that is used to sequester different materials inside a given filament. And we can define sort of a voxel unit of this filament as being in length 2 times the radius of the nozzle itself. So these are cylindrical voxels, they're not spherical voxels, but you can see, oh, I don't know why that didn't play. Let me see if I can go back, play it. You can see how this works. The printhead is moving. We've got these 4 ink reservoirs that are simultaneously spinning. The nozzle is here at the bottom. And by changing the rotation rate, this normalized rotation rate, we can change the internal structure of the filament. Now this happens to be just a pure elastomer. These regions are simply dyed with these, with a color so that you can see the internal structure. But we can also modulate the composition of those internal features. And we can print in our sort of normal way where the nozzle is perpendicular to the substrate, or as we found often, we can tilt the nozzle and it actually gives a little bit better uniformity in terms of the internal architecture, or even out of plane. And so let me play these movies. Good, they're working. And so then just simply by changing the nozzle geometry and or the rotation rate, we can start to create gradients by changing the relative rotational rate, or by alternating the sign of the rotation to create alternating regions of opposing chirality. And then if we want to create straight channels or straight designs that actually turn at corners, you'll see that this is not rotating at all. And then every time we hit a corner, it rotates in order to keep the blue on the outside and the red on the inside, right? So there's sort of higher degrees of complexity that can be built into these architectures depending on what you're trying to achieve. And so one of the examples that we had in this paper, we did dielectric elastomer actuators, which I won't talk about, but Natalie was really interested in these, what she called springy filaments and lattices. I call them architected, but same idea. You can see that during the printing process, we're UV curing this material on the fly, and the nozzle in this case is tilted. So this is really how it comes out. There's a stiff and a soft acrylic material in the ink, in the co-flowed ink reservoirs. And these have nearly identical shear thinning responses and nearly identical shear yield stresses. And what's important, though, is once they've been UV cured, their stiffnesses vary considerably, right? So we've got about a 5,000x difference in the Young's modulus of the stiff and soft filamentary features inside each of these given filaments. And this is just one cross-section that shows the blue, the stiff, and the soft material. Now, when we take these filaments and we put them under tension, we see that the Young's modulus as a function of the normalized rotation rate that changes by roughly 3 orders of magnitude here. And we can just use simple composite theory. For example, when the when there's no rotation, the stiff elements are mostly the load-bearing elements, and the mechanical properties that you test are similar to the purely stiff acrylic features. And then when you're rotating at ever higher rates, you're essentially creating parallel plates, if you will, of stiff, soft, stiff, soft. And then now when you test this, you're dominated primarily by the modulus of the less stiff material. But here you can see that the failure strains are also highly tunable because essentially as we go from something that's stiff and brittle that has a very low expansion, a very low strain to failure, to something that's highly soft, where now as we increase the rotation rate and become ever more dominated by the soft phase as we're layering that, then we get strains out to almost 100% of the initial fiber length. So by simply changing the rotation rate of these two materials as we're integrating, something very simple, right? But nature does this all the time. If you think about nacre, a shell, it's basically a brick-like structure of highly stiff features, ceramic features, tiles, if you will. Intercalated in between that is protein. So nature builds all the time with stiff and soft elements. And so this is just a way to actually control very systematically where they're located. And of course, not surprisingly, we extended this into lattice-like architectures. So not just filaments, now we're building lattices. Both ones here where you can see the stiff and soft at a normalized rotation rate of 3, or gradients where we're tuning across the architecture the stiffness and strain window by changing the rate at which we rotate the nozzle as we're printing. And with that, then again, in these three-dimensional objects, we have, again, a very large landscape of responses that we can tailor in. And if you look, each one of these are same colors are different values of the rotation rate, and in each case we have two samples that are being shown here, and that gives you some sense of the reproducibility of this method across these two sets of data. Okay, so now I kind of want to shift gears and talk about liquid crystal elastomers. This really came from, the motivation came from some of our work in embedding into soft matrices like stiff fibers, either cellulose microfibrils or these short fibers that could either be glass rods or things like silicon carbide fibers. And we started to think about, well, we saw direct observations of how we could use shear to align these kinds of architectures. And the question was, would we be able to print liquid crystal elastomers and take advantage of shear-induced alignment to program their response in these kinds of novel architectures? And what a liquid crystal elastomer is essentially it's a combination of mesogens that are liquid crystal-like. So they have these rigid backbones. And in just pure liquid crystal form, they undergo these transitions as we increase temperature. They go from a very highly ordered crystalline-like arrangement to a pneumatic liquid crystalline phase to an isotropic liquid. So they become, as you get more thermal energy, these mesogens eventually become randomly aligned. But there's been a huge resurgence in this community, in this field of liquid crystal elastomers, and one can take these rigid mesogens and they can put them along the backbone of an elastomer-like architecture that's lightly cross-linked like pure elastomers are, or you can have them as side chains or end-on configurations. So there's multiple ways to introduce these mesogens. Because we were relying on shear-induced alignment, we focused into the backbone of oligomers, which we printed, and as I'll show in a minute, then cured and cross-linked so that we would create the three-dimensional network. And as you can see here, there are many different ways in which you can do printing to pattern these liquid crystal elastomers. And we've been focusing on direct ink writing, although we do have a paper more recently that just came out with the group at Sandia, where we're using magnetic field-induced alignment in conjunction with digital light processing to also architect and control orientation. And of course, there are other methods. Some of these methods, absent a magnetic field, though, don't encode the directional alignment of these rigid mesogens. And as you'll see, that's actually quite important for many of the devices shown here, which include shape-morphing architectures, robots, actuators, and artificial muscles. And I don't even want to highlight haptic devices here because I think the time scale for transformations of liquid crystal elastomers are just far too long for haptic interfaces. So in the haptic device space, we've been focusing on dielectric elastomer actuators. That is actually a much faster response. So I talked about how we make these liquid crystal elastomers. We combine polymer chains with liquid crystal mesogens. We have cross-linkers that introduce a light cross-linking. This was actually the work of a very talented PhD student, Arta Kotikian. We designed an ink that was solvent-free. Of course, it's viscoelastic because that's what we need, and UV curable. The idea here is that we use the printing in the form of the oligomers, so they're just long chain, single chain macromolecules. And then we lightly cross-link them after printing using the UV curing, and that basically allows us to lock in the shear-induced alignment so that we don't have a loss or a degradation of that alignment. So that having that UV curing step is very important. We also do this in the pneumatic phase, as I'll describe in a little bit more detail. So here are some examples of different mesogen to amine ratios that we've looked at. The data that I'm going to highlight today is really almost in this 1-to-1 regime. So these are fairly high molecular weight oligomers, 10,000 grams per mole. If we look at the differential scanning calorimetry data, we see that there's a pretty large range of temperatures where we could work for printing, but above the glass transition temperature, of course, below this TNI value, which for these materials is around 95 degrees C for what I'm going to show first. And then we can take this data, we can fit it to a Corot fluid model, and we can get the characteristic relaxation time lambda here, which becomes important. I'm going to describe in just the next slide. And you can see that this is all done at elevated temperature. So we have coined the term hot direct ink writing. Let me go back here. This is actually heated. So this material that we're depositing is in the pneumatic state, but slightly elevated temperatures because these are pretty highly viscous. And so at this temperature, you can see that depending on the composition, we have different viscosity values, but they all fit very nicely to this value. And depending on the composition, we also have a pretty large range of relaxation times. So if we do things right, if we print correctly, we can in fact shear-induce alignment. And so we can, as I'll talk about in a minute, we can assess the orientation parameter, the order parameter. But in this case, you can see that we've printed a uniaxial thick film. And in the direction where we have the director of mesogens aligned, we get substantial contraction. So we think about these as artificial muscles because just like when we lift a weight with our muscles, we're contracting, right? There's a contractility. And in the opposing direction, of course, it's getting higher, it's expanding. And if you look at the strains associated with this contractile direction where we've encoded this director alignment, it's about 40% strain. And importantly, these can lift about 1,000 times their own weight. So they're much stronger than we are. I can't go to the gym and lift 1,000 times my weight. I can't even lift 1 time my weight. But so we have to think about how are we controlling this? So this is being heated. It's being actuated by just heating above the TNI value. As you go back to below the TNI value, you can see this very nice cyclic transformation. It's highly reversible, okay? So that also makes a very nice artificial muscle, if you will. So from the perspective of trying to understand the director alignment, we were fortunate enough to collaborate with a group. Ron Pindak led this effort at the Brookhaven National Lab synchrotron light source, and also a former postdoc, Emily Davidson, now at Princeton, was instrumental to starting this project. And then Rodrigo Tellis, a PhD student in my lab, really really did the lion's share of the work. But Emily was a co-author and a co-collaborator the entire way through the process. So I definitely want to give a shout out to her. At the beamline, we could do in operando. So as we're actually printing, we have a 3D printer set up at the beamline. We helped work with them to create a printer that would be useful for what we're doing. We're carrying out wide-angle X-ray scattering measurements. And so we have a beam size that's actually quite small, 2.5 by 25 microns. So we're able to go up and down the nozzle vertically and look at the alignment that's encoded, but also radially across the nozzle. So at the wall, you have the highest shear stresses. This is where we'd expect to see the greatest direct alignment. And of course, at the nozzle exit is also where we would expect to see the highest alignment. Now, in the perfect world, we would love to have an orientation and order parameter of 1. It's really not possible with these main chain liquid crystal elastomers, but in the isotropic state above TNI, essentially there would be no order, okay? So we're printing, remember, in the pneumatic state, so we should see S greater than 0, but we won't see S approaching 1. So what does it look like? So first of all, we did 2 different nozzle designs, a tapered nozzle design and a hyperbolic nozzle design. The taper nozzle is pretty much what we use normally in our laboratory. But because we can 3D print any nozzle, like our rotation nozzle is a good example, we created this hyperbolic design which provided an extra sort of extensional component to the flow, not just shear flow. And so what we see here, if we look at the center line position, so this is going up into the nozzle from the outlet up to 4 millimeters in height. We can see that depending on the Weisenberg number, which I totally blew past, so let's go back. This is just a balance of elastic to viscous forces. This is a scaling parameter. When this parameter is much lower than 1, we would expect isotropic features to be printed, no shear-induced alignment. When this is above 1 and substantially so, we would expect these long oligomers to stretch and become aligned. And that's what we really showed there. And this Weisenberg number is proportional to the shear of, at the wall, at the nozzle wall, the shear rate at the wall, and that measured structural relaxation time that I just showed you, lambda. So with that in mind, when we're at a Weisenberg number less than 1, you can see that we have very low order. When we go up to a Weisenberg number of basically 500, we get a very large amount of order where the order parameter is approaching 0.5. And then you can also see that in a tapered nozzle, there is a big difference in terms of the center line position values. And in the hyperbolic nozzle, it's essentially uniform across the entire height of the nozzle. So this extensional flow helps to enhance the degree of order. And then we can look across the radius of this nozzle and also ask ourselves, like, what is the variation across the internal structure? And if you want to encode a high degree of orientational order, then we essentially want a tapered nozzle, because it looks quite uniform across both the center line as well as the radius, and we want to work at high Weisenberg numbers. And so with that, then, we can see that as we characterize the bulk orientation as a function of this maximum Weisenberg number, where here the shear rate at the wall is the highest shear rate across the nozzle radius, that we're approaching sort of a steady state value of about 0.45. And that depending on the degree of alignment, we're not only changing the mechanical properties of these structures, the more aligned, the more stiff, and the less flexible, but we're also changing, and we can locally encode the actuation strain. So at low degrees of alignment, there's very little change in the actuation. We heat it up, it doesn't really contract or expand laterally. Whereas if we encode this high degree of alignment, as I said, we get about a 40% contraction along that printing direction. So that's kind of interesting, because what it lets us do at high Weisenberg number, of course, in the uniform state, we're printing these little square spiral cells, and once we heat this above the isotropic temperature, the pneumatic isotropic temperature, all of these little cells uniformly pop up out of plane, right? Because we've encoded alignment along that direction in each of those unit cells. And when they want to contract, they go up laterally, out of plane. For that same then material, we can, just by changing the rate of print speed and toggling between a low and high Weisenberg number, we can then start to encode only specific regions that will shape morph out of plane. So all of the unit cells that form the H are shape morphing out of plane, and all of the other surrounding unit cells, same design, but at low Weisenberg number where there's really no director alignment, they don't transform. So we have the ability with the same composition, just by changing something as simple as the print speed, to locally encode not the composition is the same, it's just the alignment, and that changes what regions undergo shape morphing. And as I already mentioned, these aligned, thick, printed LCEs are pretty remarkable materials in terms of being like artificial muscle-like. So this is sort of a poor man's version of a heater that's heating these. In work that I won't show, we've actually introduced liquid metal so that we can electrojoule heat these architectures on demand. But you can see that their actuation strain and more importantly, their specific work is akin to human muscles. I mean, it's the specific work value is actually akin to human muscles. The actual load that they can lift is much superior, as I already discussed. So the next thing we did was we started thinking about origami. How could we take, you could do this, of course, with the same material, different print speeds as I just showed, but we, at this time, hadn't done some of that fundamental work. And so the way we introduced origami hinge-like architectures was to do bilayers. So now we developed two different types of liquid crystal elastomer materials. One we call high TNI, so it shape morphs around that 95 degrees C, and another one that shape morphs at a much lower temperature, are low TNI values. And then we also connected these by 3D printing to rigid tiles. So these LCE features, which are either printed in such a way that we have a mountain or a valley fold, are connecting tiles that we also print out of a stiff acrylate ink. So what you're going to see here is a movie I'm going to play. Each one of these little features here is a bilayer of this material. And we're going to start heating this up. And you should see this feature fold first because it has a lower TNI, and then this one. And this is just a simple tri-layer structure, whereas if it folded together with these two hinges, it would form a triangle if they were made out of the same TNI. But because there's a sequential folding to this, because as we're heating, the low TNI goes first, we can fold this into more of a paperclip kind of architecture. So you can see that first folding, and then the second triggers. So this is just stills from that image that I just showed you. And then depending on whether it's a mountain or valley fold, we can kind of have this curvature, convex or concave, and then we can, basically start to create more interesting architectures. So with this in mind, the last demonstration that we did for this paper was what we call the robot. And it's kind of, to be honest, a little ugly. But when it's when it's all folded up, you see the defects are a little not as apparent. But what you have here are these little rigid tiles, and you have the hinges that are made out of low and high TNI materials. And interestingly, the high TNI material is sitting here in the internal part, and the outer tiles are out of the low TNI material. And you're going to see why that's important in a minute. We want the low TNI material to always stay folded, and we want the hinges, which are sort of the things that are propelling this, to fold and unfold. So, okay, it looks pretty like it starts to fold. It's trying to find this pentagonal shape. It's almost there. It's almost like I think I can, for anybody whose mom read that book to them when they were a kid. And then now these hinges are the things that are propagating, but you can see as they come out of plane, they fold back in so that they can reset to move the next locomotion, right? So the outer features are always folded because we're above their TNI value, and the internal ones are really kind of propelling the robot. So I think I have just a few minutes left. What I want to show next is a little bit of back to lattices. And here I would say that we again take advantage of the fact that we have these two disparate LCEs. We can encode in their director alignment along these printed either diagonal struts or horizontal struts. And by mixing and matching where the high TNI and low TNI struts reside, we can really change the way in which these architectures shape morph, and I'll demonstrate that for you in a minute. But I want to highlight the contributions here of Audrey Watkins from Katja Bertoldi Group and Katja herself, who helped put together a model that would be predictive, that would allow us to a priori do inverse design to encode specific shape morphing transformations. But first I'm just going to talk about the lattices themselves, and then I'm going to talk about some more interesting architectures that do sequential shape morphing. But so in order to feed the model, we did experiments to characterize the stiffness as a function of temperature for both of these materials in printed form, and also their actuation lengths as a function of temperature. So again, the higher TNI material has a higher actuation percentage, but also requires a higher actuation temperature. The low TNI material triggers earlier. With this dynamic model, they are inputting these values for the Young's modulus, which we've measured as a function of temperature, and the normalized actuation length, also a function of temperature. And from that, then, they can take an initial configuration and predict the final configuration after all this shape morphing has occurred, sequentially low TNI first, then high TNI. So let me just, I'm not going to spend a lot of time on this data. It's a lot, admittedly. I just want to say that when the struts are the same composition, so here's the unit cell. The diagonal struts here are low TNI. The horizontal struts are high TNI. This is the opposite. You get essentially a sequential morphing where they ultimately go to the final same shape, and we go from a unit cell that's equilateral to an isosceles-like triangle, because that's how it eventually transforms. And then when the struts are opposite in composition, where you have a high and a low, or a low and a high and a low, that's when things get a little frustrating, because one strut diagonally wants to shape morph earlier than the other one. And then we get a sequential morphing that's evolved by a shear-induced transformation. So these things start to twist out of plane. And you can see these are just the lattice node positions and the evolution of them as a function of temperature. So you can see this is more uniform. This one you can kind of capture that twisting. Okay, so with that in mind, then we used that model that Audrey developed to create something that was a little more random, it looks like in practice, where local regions may be more rich in low TNI or high TNI. But the idea was that this lattice architecture would shape morph sequentially from first a target shape at an intermediate temperature, where just the low TNI filaments or struts morph, to this four-arm star. So let's see if this is what we predict would happen from the model. And this is sort of the shape morphing behavior, where it starts as a circle and then goes to this sort of four-arm configuration. So in fact, we can kind of arbitrarily encode any kind of shape morphing capability. I know that we're scheduled till 4, but I'm not sure I'm supposed to go that long. So let me just end with, I don't think I'll cover this in detail. There's a lot of cool stuff here, but I'll end with whimsy. This is just the multi-material, multi-nozzle switching nozzles, where we can switch at frequencies like of the order of the rate at which hummingbird wings beat. So like of the order of 50 hertz, hummingbird wings beat at 80. But just some whimsy. This is one of our little walking robots, where again we're printing stiff and soft elements, where the flexible elements are like the muscles and the stiff elements are kind of like your bones. And you can see that we're encoding in these channels. Those are the pneumatic channels that inflate each of these features. And I might even just, yeah, you can see what it's doing. Each one of these little legs is being printed stiff and soft. And then this is it starting to like do its thing under a pneumatic actuation. This is sort of whimsy, right? So we flip it over now and it can carry weights, and it's kind of cute. I have to say, this paper appeared in Nature several years ago, and when I met with the editor subsequently at a meeting, she's like, "It was these videos. That's what got us to be excited about your paper." And I was like, ugh, not the science? Come on. But okay, we don't care about that. And to summarize, we've done some cool things in 3D printing. We've made a lot of viscoelastic this and that. We've made these multimaterial printheads that kind of enable you to really control composition and structure across multiple length scales. And although I didn't talk about it, we've done quite a bit in the translational space. This was our group quite a while ago. You might kind of take half of those people away now because, as I know, we're all at, I'm at Harvard. I haven't been able to replace some of these positions as as students have and postdocs have gone and done great things at other places. And with that, I'll acknowledge a lot of funding, some of which got yanked, some of which might come back. So we will pray every day for that. And with that, I'll just take some questions. Thank you so much.
When you fold and unfold paper, you see some plastic deformation, right? So it doesn't retain its previous shape exactly. Or if you do this over a repeated time of cycles, it eventually breaks.
Right. Yeah, I mean, the nice thing about liquid crystal elastomers is that there really is a kind of a full recovery, at least over the ranges of strains and shape morphing that we see. So we don't see any residual plastic deformation. We can unfold, fold, unfold, fold repeatedly without any real changes there. But it's a good, you're right. In a regular paper origami, you've got creases, and once you have those creases, they're there. You can't erase. I mean, the paper will never look uncreased when you unfold it. Yeah. Yes.
Thank you for the interesting talk. I have a similar question regarding the folding origami.
Sure.
So if you change the aspect ratio of tiles, do you see any interesting changes?
The aspect ratio of tiles. Sure. I mean, you're talking about the rigid tiles that we're trying to fold, or the hinges, just to be clear. The rigid tiles. That's a great question. You could see in the robot that we actually had to cut away interior parts of the tile to make it lighter so that we could actually get the thing to fold. But we haven't done a lot of work in changing aspect ratio. Obviously, the thicker the rigid tile is, the heavier the mass, the harder it's going to be for the hinge to actually actuate and move it in a way that would complete the folding sequence. But it's just not something that, honestly, we've really evaluated in any detail. So, yeah.
Great talk. I wondered as you build understanding between the materials and the properties, et cetera, and that trigonal pyramid thing that you put in the front, can you go in the inverse direction where you use modeling to achieve what you want out of the material?
Yes.
From the understanding that you're building.
Yeah, no, the idea of using inverse design to guide, that one little simple example I showed of the square and the circle, like the four-arm star, that is the dream. And in fact, let me just pop one forward. No. Okay, I thought I had kind of important slide here. Yeah, it was hidden. This slide kind of is the vision, right? If you can build voxel by voxel, which is kind of where we're going to, right? Essentially, there's kind of an infinite number of things you could build, and I've shown you that our materials palette's quite broad. So we can put any material, in theory, with any property in any location. That is not going to be done Edisonianly. We've got to have a combination of sort of machine learning with, constitutive models, finite element models, all giving us target designs for whatever it is that the property performance you desire, right? Now, it's not true uniformly that all materials are compatible, so it's not like infinitely true that we could print any material next to another material and it would be compatible, interfaces would adhere, et cetera, et cetera. But that's kind of where we're thinking. So it's actually a really great question. Yes? That's the dream. Yeah.
Poisson ratio control,
Yeah.
can you imagine that you could actually alter properties instead of just the dimensions? For example, you have enhanced, say, thermal in one direction, enhanced electrical in the other.
Yeah.
You can control that.
Yeah, I mean, that kind of comes back to that vision of voxelating, right? So you can start to combine structural elements with multifunctional elements. I didn't talk about some of our liquid crystal elastomer work where we're encoding or embedding inside liquid metals. We're using those for joule heating, but liquid metals could also be like, you could have a dynamic antenna, for example, right? Where as you're shape morphing, the frequency that the antenna is able to transmit is changing, right? And you can dial that in. Yeah, I think there really is almost a limitless set of possibilities. And honestly, our work is, as you can see, is pretty simple concepts, simple ideas, right? But I think it opens up, I would hope, and many people are fast following and doing far cooler things than we've done. But I would say, yeah, it's just kind of opening up people's ideas, basically.
Follow.
Sure.
Poisson ratio is, of course, in 2 dimensions, but
Yeah.
can you imagine a 3D version?
Yes.
Where you
Yes,
Yeah.
and
And
so
you have a 3D version
yeah,
of
Ole
Poissons.
Sigmund has some beautiful 3D unit cell designs to control that. They're often multi-material, so they're not just 3D, they're multi-material. I would say that our embedded printing method could realize those, but there are some limitations with embedded printing too. I mean, you can think, and I didn't go into this in detail, but wherever you print something like that zone, like you can't cross a filament you've already printed. There's also designing the matrix so that, as you're translating the nozzle, you're not dragging the either printed feature or opening up defects in the matrix. So it is actually quite challenging. I think Tim might be, using a light-based 3D printing method to realize some of these complex architectures. In many ways, that has a lot of advantages. It's often challenging to do multi-materials in that motif, but there are advances being made there too.
I have the mic, yes. Thank you, Jennifer. This was very stimulating talk.
Thank you.
So you mentioned that you can print any desired property in any location, right? That's
That's the holy grail.
that's
Sure.
yes. Now I know this is basic science, but to what degree can this be scalable?
Yes, that's a great question. So I think one of the motivations behind the multi-nozzle, multi-material array printing, which, I think it's on the next slide, so I can just sort of hit play here. And you can see, like, we've done up to 128 nozzles. So something that takes 24 hours to build, right? If you have a 64 nozzle array, you're down to, like a half an hour, right? So, 3D printing can be scalable as you go to multi-nozzle arrays. And obviously, if you think about digital printing now, you can order from, Amazon and get your book printed and then, next day delivery. That's because they're using these, million nozzle arrays for inkjet printing, right? So we are now thinking about how to take some of our concepts for viscoelastic filament printing and bring them into a paradigm that's drop on demand, but that's viscoelastic. Because the challenge with inkjet printing for printing functional materials or even biological materials is the feature sizes are quite low, the shear stresses are quite high, and you can't put building blocks above a few nanometers through a nozzle without clogging. So I think I just swallowed the bug. All right. Anyways, but that, being able to array many, many nozzles is what it's going to take to be commercially viable, right? If you want to do injection molding, it could be, seconds to make a complex three-dimensional part. So how do you get printing to seconds? And there's people, working on that, certainly. Yeah, right.
Thank you for the fascinating talk. My question has to do with chemical engineering. Have you thought of printing membranes? Because that's going to be holy grail, part of the holy grail for chemical engineers.
So we do have some, like the smallest features we've printed are on the order of a micron in feature size, and that was with an early demonstration with our polyelectrolyte complexes. So I take particles out, just print these polyelectrolyte inks, almost like spiders spin their web. That was the concept. And we were able to print 1 micron features. If you also then build in internal structure, I think you can get to these higher surface areas, and if the building blocks themselves might be zeolites or other things, like it gets very interesting very quickly. It's not something that we've spent time on, but love to talk with you because I think there are real opportunities.
Yeah, because you can control domains. If you
Yes.
can control domains, you can do membranes.
Yes, it's a very good point.
Yeah,
Thank you. And just like with asymmetric membranes, we can print in solvents that drive that kind of phase separation, anisotropic phase separation. So you can also consider about having structured filaments that have porosity gradients across. So there are kind of cool things that could be done there. Yeah. Here, let me help you.
Thank you. Very nice stuffs, cool stuffs. I have already seen a lot of stuffs. I covered most of the work in our review. So I have a question. Directing writing has materials diversity, but it has drawbacks also. Compared to materials jetting or stereolithography, resolution is poor, yeah? And second one is layer adhesion. When you make a green state, that's a one adhesion, you will find very nice stuff, but when you dry it, it becomes separated, yeah, sometimes based on the material system. Another is anisotropy, because low resolution, high anisotropy. So have you think on that, like when you go for structural application particularly, this is a big...
Yeah. No, I think you've raised a number of points. I think every materials manufacturing platform, whether it's traditional or a 3D printing modality, whether it's light-based, ink-based, there's always strengths and weaknesses, right? I mean, we have a lot of collaborators that come to our lab and say, hey, we'd really like to work with you to print this. And my first thought is always like, what can we do to avoid printing that? Like what is a better method? Like microlithography, molding, et cetera, because it takes time. I mean, this isn't like a plug and play, like you just hit, a button and it prints. Like it's a lot of work to get the inks and all these things to play well and print well and so forth. And you're also right that if you're, printing in plane and you're aligning something in plane, you have a z-axis problem where it's weak as you go out of plane. Like if you're doing a fiber reinforced composite, that was actually part of the motivation for us to do the rotation nozzle to begin with, to homogenize the fillers and be able to locally vary the mechanical properties in structural composites. So, but nevertheless, I would be the first to agree with you that there are many limitations of direct ink writing or any of these methods that I described today. But there are also some key advantages. Yeah, fair. It's a fair statement.
All right, one last question from Ben.
You just need more smart people to work in this area and do better things than we have. Exactly.
Thank you, Jennifer. So very nice talk. So I have one question. So following Maksad's question, so we know DIWs like
Sure.
a process with low precision. So in terms of the future development for bioprinting, so if we go to organ printing, like even do single cell manipulation, so Then in terms of precision, for the extrusion-based, what's going to be the
Yeah.
future direction? Because
Yeah.
I did in my lab, we did some like laser-induced forward transfer, laser-assisted bioprinting.
Yes.
So, but I'm
Yes.
not printing really cells. I'm kind of trying to do
Anything.
something for the hydrogels. So I'm just curious, hear some, thing from you
Yeah.
for future.
Okay, first of all, if you were to try, okay, let me answer this question in sort of the way I would if I had presented anything that we're doing in biospace. And let's start with like any vital organ, heart, kidney, liver. They're made of roughly 20 different cell types. And in order to get function, you really have to put each cell type kind of where it needs to be, because it has an architecture just like these materials, these non-living materials do. To print single cell resolution or put a cell exactly where you want in three-dimensional space, we did the calculations. It would take like longer than gestations, like longer than, to create a 100 milliliter size organ, which is the size of my fist for a kidney, heart, etc. It takes months. Cells live in your printer for 1 hour. If they're not perfused after that, after printing for an hour, hour and a half, they die. And if you're going to print a whole organ, you have to be able to not only print it in an hour, but you have to be able to immediately take it off the printer and put it into an incubator and perfuse it, which is why the vascular piece is so critical, which I kind of alluded to at the beginning of the talk. So our original idea when we first came to Harvard, super naive, never done anything in cells, is like, we're just going to print cells and gels, blah, blah, blah. Well, first of all, the cell density was super low. We could vascularize it, great. But we started to realize, like, we're never going to print 20 different cell types, blah, 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 and get them where we want, et cetera, et cetera, et cetera. At the same time, this was back in 2013, 2014, the whole field of induced pluripotent stem cells, Nobel Prize, 2007, Yamanaka, got it. Organoids started to come. So maybe some of you have heard this term, maybe many of you have not. Organoids are essentially these little mini organs in a dish. They're like a 0.5 millimeter in diameter. They're made of many cells, but you take pluripotent stem cells, you make an aggregate of those, and then you sort of feed them a cocktail, just like they would get, during embryogenesis. And these individual cells in this aggregate can form brain tissue, they can form kidney tissue, they can form cardiac tissue, and they do it pretty exquisitely. Like, they actually form the architectures, like in the kidney, which we're working on. We use those as the building blocks. So the idea, coming back to this comment, like, do you really want to print everything? Can we do it a different way? Let biology do 90+% of the organ for you. Just top down the vessels. I mean, that's a very simplistic response to your question, but that's how we think about it. Let biology do the work as much as possible, until somebody really, really smart is able to print an hour, 100 milliliters, and put every cell exactly where they want them. I mean, you'll make a lot of money if you can do that. But you'll have to spend a crap ton of money to do it. Our first Swift paper probably cost us $1.5 million, just to give you an idea, just for one paper. So many cells, almost a billion cells, and so many reps of making that. Don't get me started. So it just requires a lot of capital to do these kinds of things at scale, to be honest. Yeah.
All right. Thank you.
Okay.
So much.